Let's look at another example involving a tangent plane. Now, in certain instances, we're just interested in understanding where the surface may have a horizontal tangent plane. This is basically the problem from Calculus 1, where you look for horizontal tangents. So again, we're going to have the idea of critical point in Calculus 3, like we had the idea of critical number in Calculus 1. So everything is aligned very nicely. So in this particular problem, the surface is somewhat interesting. Z is equal to xy plus the reciprocal of x plus the reciprocal of y. So now we're thinking, okay, are there points where we would actually have a surface normal that points what up 0, 0, 1 or 0, 0, negative 1? And of course, the problem is set up so that we do get a point. So let's go ahead and work with this. Now what we see is we need an implicit equation, which we always use with the tangent planes. So F will be xy plus x to the negative 1 plus y to the negative 1 minus the z. And of course, that's going to give us the negative 1 with the partial. So we'll have a solution here that will be fairly straightforward. So in order to look for the surface normals, we look at the gradient. So of course, this is our implicit equation. So we have fx will just be the partial relative to x. So we get y minus x to the negative 2. And if you will, y minus 1 over x squared. This is starting to look like college algebra problems. So the y partial will give us x minus y to the negative 2, which is x minus 1 over y squared. And then, of course, the z partial is just negative 1. So this implies that we're looking for a surface normal of this form, 0, 0, negative 1. And of course, the coordinates here give us that surface normal. So this would mean that our x partial and y partial must be identically 0. So let's go ahead and compute that. So now we've got fx equals 0 if and only if we look at the equation, y will equal 1 over x squared, and fy is equal to 0 if and only if x is equal to 1 over y squared. So at this point, we can just use basic substitution. Notice that we can replace the y here with the expression of y here, but this is in the denominator. So if you want to call this equation 1 and this equation 2, we would have by 1 that 1 over y is just equal to, in this case, x squared, and therefore, through squaring, 1 over y squared is just x to the 4th. So now with 2, we'll just do a substitution. 1 over y squared is x to the 4th. So we have x to the 4th equals x if and only if x to the 4th minus x equals 0. And of course, now we enjoy our factoring. No constant term. So equivalently, x times x cubed minus 1 equals 0. So now, of course, x equals 0 by zero product, we discard by nature of the original surface. That would not be a point on the surface. So we discard x equals 0. So that just leaves x cubed minus 1 equals 0. Of course, that's a difference of 2 cubes, but there's only one real 0, the other 2 being imaginary. So this would imply, or equivalently, x would equal 1 for a real solution. Nothing wrong with the imaginary, but this isn't complex variables. So now we've got a value for x, but clearly, if we just go back to what we have here, number 1, if y is equal to 1 over x squared, this just implies that y equals 1 divided by 1 squared, which is clearly 1. And now we can go to our original equation. So then, using z equals xy plus x to the minus 1 plus y to the minus 1, we'll just substitute 1 for x and y. This will give us 1 times 1 plus the reciprocal of 1 plus the reciprocal of 1. All ones, obviously, so 1 plus 1 plus 1 is 3. So this is an interesting problem that's rigged to give us the single point of the horizontal tangent. So therefore, we are left with the point 1, 1, 3. And this corresponds to a horizontal tangent plane. So an interesting problem, but very straightforward. And we are done.